Hello everyone, today I'm gonna explain this question which requires ice table to solve the concentrations at equilibrium. Okay, so let's start to sort of the information. Okay, so for this particular question, right? Okay, so let's start with see what's given we're looking for. Okay, so the given information. Okay, so we have initially, right? So as we said, once you see it's initially, you go, I probably need ice table, right? Okay, so let's start from there. Okay, so you have the concentration of water initial, so that's 2.8. Okay, and you also have the initial concentration of SO2, which is 2.6. Okay, and then you have a Kc value. Okay, so Kc value over here is 1.3 times 10 to the negative 6. You go, that sounds good. I should be happy about this. Why? Because this equilibrium constant is small. Okay, so which probably tells us you could use small approximation. Okay, again, this is just a mathematical right method will help you to use, then you can that will help you reduce the difficulty of calculation. Okay, so other than that, in terms of analyze this question, the chemistry part is still the same, and then just according to what we have been dividing into situations, this is actually situation 5. Okay, so use small approximation. Okay, so that's what I have, and then we're looking for the question itself is only asking you the concentration of H2S at EQ, right? So at equilibrium. Okay, so that's what we're looking for. Okay, so these are the direct information given from the question. Okay, so let's go. Okay, we already know we need S table, and let's start to set up with the balance equation. Okay, so again, this is my own habit. I like to do this so that I know exactly what I'm dealing with, but of course you always could do the way you feel most comfortable with. Okay, so this is what I have. Okay, and then I'm gonna start to set up my S table. Okay, so S table. Okay, okay, so let's see. Sorry for the line. Okay, so that's what we have. Okay, I'll fix it. Okay, a little better. Okay, so ICE. I represents initial. Okay, so one more time, we already know the given concentration, so that you have 2.98, you have 2.6. Okay, you go, what's here? What's this two? Again, if you're only giving initial of one of the two reactants, then mention the other two, then that's that's a implied information. That means, I'm sorry. Okay, so which means these two are 0, right? So that means initially you don't have any of those. Okay, so these are 0. Okay, so that's something we know, and then now from this point we're supposed to use the given information and solve for it. Okay, so that's what I have, and then you go, what should I do from this point? Okay, so as I said, after you have this initial, you need to decide Q. Okay, so that's also important for you to calculate for. Okay, so let's use this color. Okay, so the first step, you're gonna calculate for Q. Okay, so let's see what the Q value should be. Okay, so it's still product. Okay, so that'll be product H2S squared times O2 to the cube divided by, all these are initials, right? So that's the condition where we're given. That's our starting point. So that's our initial. Okay, SO2 squared, all these initials. Okay, so then you have 0 times 0. Okay, divided by whatever 2.8 squared times 2.6 squared. This equals to 0. Okay, so you have Q equals to 0, and the second step you're gonna compare, right? You're gonna compare Q with K. Okay, so Q is 0. Let's see what's K. Remember, k is 1.3 times 10 to the negative 6, even though that's a small number, but that's still bigger than 0. So q is smaller than k. Okay, so once we could decide this, you go, this sounds about good. Okay, so this is good. Okay, so that's 0. Again, I'll just put the values here and you see how I compare, right? Okay, so that's q smaller than k. Remember, once you see this, you go, I could decide the direction goes to the forward direction, right? Okay, so the reactants will be consumed. You're producing product. Okay, so therefore at this stage, right, you could go, okay, so then you go, okay, I'm gonna say, I feel very comfortable to say, right, I'm consuming or consume a reactant. Okay, so which means, right, means for the change for reactants is going to be what? Negative, because you're using it, you're consuming it, right? So the change for product is going to be what? Positive. You're making more product up. Okay, so that's what you have. And now that's very good, right? So we can do negative, positive, and positive. Okay, the other thing you have to remember from the lecture, right, we say when you have change, goes back to what? The coefficients. Okay, so which means this will be 2x, and 3x. Okay, so the sign goes decided by the relationship between q and k. Okay, so that's what we can decide. Okay, and now it's not so bad. We can just, add up the initial and change. Then we can fill out what's happening at equilibrium. Okay, so then you could have 2.8 minus 2x, then you have 2.6 minus 2x, then you have 2x, 3x. Okay, so as I keep on saying, right, what do we need to proceed? We need this, right? Equilibrium. You go, why? Because we have one more information we haven't used, right? What's the information we haven't used? Kc. Kc represents what? Equilibrium constant. Okay, so in order to express Kc, okay, so Kc, what do we need to use, right? So we'll do this, right? So Kc is the same expression, right? So that's actually borrow it. Okay, so it's the same expression but slightly different. Okay, so I'm gonna borrow it so to save some time. Okay, so I'll put over here, but instead it's not initial, is what? Because we're talking about equilibrium, all this concentration you use will be at equilibrium. Okay, and then that's why from S table we needed these numbers, right? We needed all those. Okay, so we're gonna use all those and put into this expression. Okay, so that's what we're gonna use. Okay, so then go by the table, then you have 2x squared times 3x to the cube. One more time, I'm directly following over there. Okay, I guess I'll do this so you can see it. Okay, and then on the bottom, on the denominator, you'll have 2.8 minus 2x squared times 2.6 minus 2x squared equals to 1.3 times 10 to the power negative 6. Okay, remember we said you can use small approximation. Okay, I'll just explain it one more time. The idea is, right, because the change is going to be so small, the change we're talking about is on the denominator, right? So when you have a change, or you could say when you do addition or subtraction. Okay, so that will be a better way to describe it, right? So when you do a small change, which means you're doing addition or subtraction, so it's like if I have $1 million. Okay, if I have $1 million, if I use $1, so that means I'm gonna subtract 1, right? So I'm gonna minus 1. Do you think that change, that $1 will make a huge difference to my $1 million? Probably not, right? Okay, but if you do go, oh, I have $1 million already, and then I made another dollar today, do you think we feel a huge difference? I have $1 more or less? Not, because the change is so small. Okay, so that's why when you do addition or subtraction, with the x, right, with the change, if we know that will be small, then we could consider that change will be it could be a negligible, right? So you don't need to worry about it. Okay, so that's why over here on the denominator, right? Okay, so you have that change. Okay, so in that way, you could use small approximation. You can just consider that will be 0. Okay, so that's 0. Okay, but the value, right, the constant still there. Okay, so that's something make sure you understand. Okay, so from this point, okay, so we're gonna continue. Okay, so on the top, right, on the numerator, okay, so you will have what? You have 4x squared, okay, times 3 to the power of 3. Okay, 3 to the power of 3. Okay, so that will be 27. Okay, is it? Yes, 27. I'm sorry. Okay, so that's what you have, and then on the denominator you have 2.8 squared, 2.6 squared, and equals to 1.3 times 10 to the power of -6. Okay, and then you're gonna solve this. Okay, so you're gonna put x on one side, the rest of the number on the other. Okay, so you have x to the power of 5, and on the other side has 6.38 times 10 to the power of -7. Okay, so then you're gonna solve this. X equals to 0.058. Okay, so that's x value you just solved. Okay, and then remember, you always need to check, you need to double check if small approximation will be valid. Okay, so if a small approximation is valid. Okay, so in order to check this, we're gonna do this, right? So you're gonna have 0.058, okay, divided by the initial concentration to time 8. I'm sorry, 2.8, okay, and then times 100, okay, and then after you double check this is 2.1, smaller than 5%. So that means we're good to go. Small approximation is valid. Okay, so it's good. Okay, so it's good. Okay, so it's good, and then it's good, then we can use this value. Okay, so x is 0.058. Okay, so if you look at this table, right, x is, I'll just put over here. Okay, so we solve for it. X equals to 0.058. Okay, and then what we're looking for this question, we're only looking for one, right? H2s. Okay, so we're looking for basically 2x. Okay, so you're just gonna solve for that. So 2x will just equals to 0.115, approximately is 0.12. Okay, so remember, you're gonna report exactly the number of sig figs the question is asking for. So if it's 0.12, just say I'm asking for 2 sig figs. So then you're gonna report 0.12. Remember that 0 up front, that will be not significant, right? So that 1, 2, those two values are significant. Okay, so this will be this question. Okay, so this question, how you solve the question by using small approximation. Okay, so again, small approximation applies to when you do addition, subtraction. Okay, so I know in the lecture I mentioned, right, most of the cases is on the denominator, but remember this really applies to when you have the change also, right? So this is how you do solve questions by using small approximation. And thank you for listening, and then hopefully this is helpful.